Let us continue our analysis of the conics in the polar system. Today, our goal is to analyze a polar equation and graph it using the polar system. And from there, we'll step back and we'll make some comparisons to the rectangular system. There is an assignment on Google Classroom /15 problem set. Please do that. If you have any questions about it, fire away an email to me or communicate via Google Classroom. So where were we in the last class? We had derived this particular equation right here based on the definition of a conic. We recognized that the directrix in that definition was running vertically to the left of the pole. We then talked about how the trig function that shows up dictates the movement of the directrix from the pole, and therefore by default the orientation of that particular directrix. If it's cosine, the directrix is moving vertically. Positive, it's gone to the right. Negative, it's gone to the left. By extension of logic, sine implies that it's moved vertically, which means it runs horizontally. Positive sign is above, negative sign is below. But the most important thing, if I'm in polar form, is to recognize that all four of these equations call for this constant of 1 to be there. So let's say I was given a polar equation and asked to graph it. My first issue with this is, number one, I look at it and I already see this, I see that, and I already know where the directrix is. I remind you, the directrix has a special relationship between the axis of symmetry on the parabola, the major axis of the ellipse, and the transverse axis of the hyperbola. It is perpendicular. The direction of this dictates the direction of those potential other three. Important thing to know. So first of all, let's do some numerical manipulation here. So I need to get this to be a 1. That is the beauty of the equality properties of algebra. I will do that very easily by simply dividing the top and the bottom by 3. Essentially, I've taken one side of the equation and really just multiplied it by 1. This now is in a form that makes sense to me. This, by definition, is E times P, and this, by definition, is E. So recognizing that the eccentricity is 2, and remember, the value of the eccentricity, whether it's less than 1, equal to 1, or greater than 1, dictates which conic it is. Recognizing that the numerator I now can interpret as that product of E and P because this is 1. I'll take my E value, I'll substitute it in. There it is, and that therefore tells me my P value. For those of you who may not remember, P was the distance the directrix was from that pole. We'll talk more about that. And what's great about this particular process and mathematics in general is there's very actual few ideas you need to worry about, but there are thousands and thousands and thousands of potential situations that they may show up in. And you guys have to learn to be a bit flexible. So what do you see? Well, I still see a polar equation, and I'm wondering what this particularly looks like. But it does not show up like any of my previous 4 at all, which only calls for sine and cosine. That's okay. Identities. There's a relationship between cosecant and sine, and that is that they are reciprocals of each other. So I can easily jump to my reciprocal identity. From there, just use the laws of mathematics, multiply the top and the bottom by sine, and now I'm to here, and I recognize, oh, this is one of the equations of a conic. It already is equal to 1. Therefore, I can interpret the coefficient of sine to be E and the numerator to be E times P, which allows me to, once again, E is 1. Remind you, the minus signs are just talking about directrix direction, whether it's moved to the left or the right in cosine, or up and down in sine. EP is equal to 3. Therefore, substituting in a 1 in for E allows me to know that P is equal to 3. So be flexible. Always be flexible and think about everything you've learned. Ready? Everything you've learned in the hypothetical previous 18 years of your life, you should be able to use it any single time, ladies and gentlemen. And yes, the upper division teachers do expect you to remember something you were taught before. There's your college life lesson of the day. Let's just take this top one and let's start graphing it and see if it's easier or it's more challenging in the rectangular system. So I got to here. Cosine minus implies the directrix is moving vertically to the left of the pole. I know exactly where this is. It is a distance of 3/2 from the pole. So I think I have a little, there it is. I wrote it in rectangular form. This is a line of x is equal to -3/2. It's going to help me out. So what would you do first? Well, I'd think about my definition, first of all, the eccentricity. Knowing that it's more than one, that does tell me it's a hyperbola. Please reference that from a previous lecture. What's next? Well, I think the easiest thing to do is just locate one of my foci. How do I know it's there? That is according to the definition of the conic. We always place that focus in the definition at the pole. So there we go. I've shown you its coordinates in polar coordinates, r comma theta, and I've shown you its coordinates in rectangular, x comma y. And I'll do this continuously for all these points right here. We'll figure out which one is easier. Now, I know some of you might be thinking they look like the exact same thing. That is because I've chosen to express theta. Remember, r, theta. In this case, theta in radians. To avoid that, I'll use degrees for all my other angles. What does this tell me? This tells me I'm going to rotate an angle of 0 radians. I'm going to not go forward at all. That leads me to right there. What point would I find next? Well, this is the directrix, and since it's a hyperbola, the relationship of the transverse axis is that it is always perpendicular to the directrix. Which points of the hyperbola are actually on the transverse axis? Well, that's the vertices. So what angle is this one? Well, that's an angle of 0 degrees. What angle is this one? Well, that's an angle of 180 degrees. I think what I'm going to do, I'm going to take those two angles, I'm going to plug them into my equation. We're way back to plug and chug, like back in the days of Algebra 1. And I'm going to find my respective distance of r. So plugging in 0, the cosine of 0 is 1. 1 minus 2 times 1 is -1. And 3 divided by -1 is -3. So that tells me that one of the vertices is at -3 comma 0 degrees. What does that mean? That means I'm going to not rotate at all, and a negative r value means I'm going to move in the opposite directions. That puts me here, a distance of 3 away from the focus, which is at the pole, moving in an opposite direction of 0 degrees. That easily corresponds to -3 comma 0 in the rectangular system. So there we are. Without any particular formula, just intuitively, I've now recognized how these two relate to each other. So let's pick our vertex, and let's put it at a -3 comma 0. Now, I'm guessing it's right about there. How did I get that? Well, I already know that this is at -1.5. Therefore, this, of course, would be doubled at -3. What would I find next? Well, I'd find my other vertex by plugging in 180 degrees. Cosine of 180 degrees is -1. 1 minus 2 times -1 ends up being 3. 3 divided by 3 is 1. So my other vertex is located at 1 comma 180 degrees. What does that look like? Well, that means I'm going to rotate 180 degrees. And then since r is 1, I'm going to move in that direction a distance of 1. That puts me right about here, which corresponds to a rectangular. I'm just going to estimate it. Coordinates, in this case, exactly at -1 comma 0. That's what I would do. That focus, recognizing which conic it is, I definitely go straight to my vertices. How am I going to find the center? Well, what's the relationship between the center? The center is the midpoint between the two vertices. So what's directly in between this point and that point? Well, in this case, I'd probably think about it in rectangular terms, and I would say that the center must be located at -2 comma 0. That's its rectangular form. Now, of course, there is no unique way to express a point in the polar system, meaning I can express it many, many different ways. We talked about the notion of these periodic functions. So I've just decided to express it with an angle of 180 degrees. So I'm going to rotate 180 degrees. I'm going to go forward 2 points. So that tells me my center is going to be at about 2, 0, which I'm just going to place right about there. What would you find next? Well, in this case, I probably can find the other focus next. How do I do that? Well, I know the distance from the center to the focus must always be the same to either foci. We've talked about the importance of the center being a midpoint. So the distance from the center to the focus, I'll probably do rectangular in this case. The center is at -2. This focus is at 0. So I need to move 2 more spaces the other direction. And that leads me to a rectangular coordinate of -4, 0, which I've expressed as 4, 180 degrees in polar form. Notice I'm flipping and flopping from polar form or to rectangular form, or choosing one over the other as I try to figure these out. So here's my other focus. Now let's just try to eyeball it to the best of my ability. So there's my transverse axis. Now, what about A's and B's and C's and things along those lines? So, ladies and gentlemen, it is true I can go to rectangular form. And remember, for hyperbola, b squared equals c squared minus a squared. I figured out a is 1 and c is 2, and that's from looking at all these values. And then I can figure out how much b is equal to. That gives me the endpoints of the conjugate axis. It allows me to find the asymptotes. But how about in this case, I just think about just really polar form. It's all about angles. I know for a fact that the 2 branches of the hyperbola are symmetric to each other. So I'm just going to find 2 more critical points of the hyperbola. And since I know the hyperbola is going to be opening horizontally, look at these points, it tells you that, because the transverse axis is horizontal. You should understand that. I think I'm going to choose this angle, 90 degrees, and this angle, -90 degrees, or 270, or however you want to think about it. So I think what I'll do is I'll plug in 90 degrees. The cosine of 90 degrees is 0. 1 minus 2 times 0 is 1. 3 divided by 1 is 3. And that leads me to one critical point is going to be at angle theta of 90 degrees. The R value is 3. So I'm just going to kind of move on up here. Plugging in 270 degrees gives me also an R value of 3. So that means I'm going to eyeball it and move on down there. So a little different in the polar system. I'm going to find just some critical points and understand the concept of symmetry. I'm then going to the best of my ability here, let's see if I can do this. I'm just going to eyeball in that hyperbola. There it is right there. I'm going to understand that there is branches that should be symmetric. So there's that flipped over. I'm going to go place this at the other vertex like that. And I'm going to view what I got. I have a perfectly done graph of a conic in the polar system, flipping and flopping between polar and rectangular for whatever purpose I need, and being very flexible about how I graph these. Think about this, and we're going to investigate the next class how we can use rectangular form if we wanted to. Have a great day.